Hi! I originally scheduled this video to be about adding an HC-SR04 Ultrasound Range Sensor to DDD, my DIY dev droid. Then I started to get rather intrigued at what you could do with lots of these sensors. So this video is going to look at using these sensors for range, calculating distance to a target to the nearest object in front of the robot. I'm going to look at two strategies for code to use these devices, using interrupts in C++ and using the Raspberry Pi Pico's PIO capability, programmable input-output. Then look at how we can use these strategies with four sensors set at 90-degree angles to each other. That starts to use a lot of GPIO pads from the Pico, which led me to look at sharing the trigger pin for these devices. Stay tuned to see if that works. Let's get the targeting system up and running. After all, we can't all rely on the force. And please don't forget to like the video and subscribe. I really do appreciate it. This video is sponsored by PCBWay. PCBWay are a great partner for any maker able to manufacture PCB boards, undertake 3D printing or CNC builds, as well as sheet metal fabrication and injection moulding. The services required for any droid building project. PCBWay also hosts pages on makers' projects, so why not check out what other makers are building? The HC-SR04's range sensor is ultrasound measurement of distance. Really? These devices are really quite cheap and fairly easy to get hold of. They are 5-volt devices though, so they require a 5-volt power supply, and their output signal, crucially for us working with Picos, is 5 volts. So we're going to have to handle that later. There is actually a new version of, or new to me anyway, of the HC-SR04 called the HC-SR04P, which is a 3-volt device, which we could plug directly into our Pico. Unfortunately, I didn't know about them until I was researching this video, so all of the ones I'm using are actually 5-volt devices, which is a little bit of a pain. But if you're buying into these fresh, I really suggest going for the 3-volt device to work with Picos. It'll save you a lot of hassle. So a range sensor, what is a range sensor? Really, well, this is how we are going to sense distance to an object. So our HC-SR04 sends out an ultrasound pulse and then listens for an echo response. So to work with the HC-SR04, we need to send a trigger, which is a simple pulse to tell it to send out that pulse. And that will work fine as a 3.3 volt pulse. Nice for our Pico, so no hassle there. It needs to be 10 microseconds in duration, so we will need to do a little bit of timing to make sure we're just providing a trigger signal that is 10 microseconds across. Then the HC-SR04 will then send out this pulse to this device and get back the echo, or hopefully. In fact, it does that 8 times and then gives you some sort of combination of those, presumably some sort of average. I don't know quite what's going on this chip, but that's what it does according to the spec, is doing that 8 times and then giving us the output. And the output then comes back as another waveform, another squared waveform. And this time it's of course going to be 5 volts, so we're going to have to handle that in a second. And we're interested in the amount of time that signal was high for, and that is the time it took for the pulse to actually go out from the sensor and the time that the echo took to come back. So in actual fact, it's twice the time that sound would take to pass across that distance. So our HC-SR04 is a 5-volt device, and I'm going to drop it down to 3.3 volts before plugging it into my Pico. I could get away without doing this, to be honest. Most of the inputs on a Pico are actually 5-volt tolerant, with the exception of the ADC GPIO pins. So as long as you avoid those, you can get away with it. To be good and to allow me to actually plug it in anywhere I want, I am actually going to use a voltage divider. When we're connecting it, the trigger is fine. I don't need to do anything on to convert the trigger. We can just plug the trigger connection straight into any of the GPIO ports on the Pico. For the echo that comes back, that's 5 volts, so I'm going to use a voltage divider circuit using 2 resistors to just drop that to a 3.3 volt range. Let's have a look at some code then. As always, all of the code that is on GitHub, and I've got a repository just around my experiments with the HC-SR04. This isn't going to be just simple get it working, because there's a few things I wanted to try and explore. So there are 4 separate projects here. One to look at how to actually just interface directly to an HC-SR04, and then how to actually use 4 of them at once in 3 separate little strategies using interrupts, PIO and shared triggers. We'll talk about that as we go forward. So most of the software stack for what we're going to do in the experiments is really just the Pico with C++ using the standard SDK. Easy stuff, nothing complicated. I'm going to use one library though that we'll talk about in a bit, and that's a library from Daniel Garcia-Briseno, who's done a PIO library for talking to these HC-SR04s. And I'll talk about that in a bit and why that's a potential advantage in some situations. So over in Visual Studio, let's have a look at the project. And the repo here has a number of projects in it. Let's start by actually having a look at GPIO int, which is the basic one we're just going to read from a single device. I've put all the code around the HC-SR04 into a range class, which is here. And so what we're going to do is we're going to instantiate this, and we're going to give it what is the trigger pin it's to use and what's the echo pin it's to use. And then we can ask it to trigger, and then we can read back what the measurement is in millimeters. And I'm using some of my classes to handle GPIO callback here. So I've need to define an interface for the handle GPIO so that I'll get a response back that the GPIO for echo has gone high or gone low. And that's using my GPIO observer class here, and this is a GPIO observer. And it's using my GPIO input manager, which is what is doing all that. The reason I use that is because using that singleton class allows me to have multiple callbacks of GPIOs. The standard callback for a GPIO pad change on the Pico can only have 1 function per core registered. So we need to decouple that a bit so that we can have a number of these classes instantiated. So I'm using this observer and input manager pattern, which I'm looking at using a number of my other projects as well. We're going to store the trigger pin and the echo pin details. And the other thing we're going to store is we're going to store this, the time stamp when a event, or when the echo pin goes high, which we'll call the start of echo, and when the echo pin drops again, which we'll call the end of echo. And we use that as our mechanism for calculating the amount of time, and therefore distance. So let's have a look at what's actually going on in the C++ part of the class. Well, the constructor's not doing anything particularly clever. It's just storing those trigger and echo pins. It's initializing the trigger to be an output, because that we're going to want to be able to send values out of that. And it's going to add an observer so that we want to observe anything going on this echo pin. When we then come and ask it to trigger, so we want it to send out that pulse, what I'm doing is, and I'm doing this in a way that I don't like very much. In fact, I don't like it so much, I'm going to change it in a second. But for now and for simplicity, I will explain, we're just going to basically raise the value on that pin. We're going to sleep for 10 microseconds, and then we're going to lower it. That should give us a very simple square wave pulse, which will trigger the HC-SR04 to start its echo cycle. So then what's happening is we're going to get responses back from the device of when the signal goes high and the signal goes low, and we're going to do that through this handle GPIO function. So first thing I need to check is, well, first thing I'm going to do is just capture what is the current timestamp. Where are we at currently in time? Because that's all I'm actually going to keep storing. Then I'm going to just check to see that the GPIO I've been given a callback on is actually my echo pin, just in case. If it is, then if we're a rising edge, then let's store the start time of our echo. If it's the falling edge, then let's store the end time of our echo. Easy. So the distance calculation is really, first of all, let's just check that the end time is greater than the start time, that we actually did get an echo. If we didn't, then I'm going to return -1, that actually I have no idea what the distance is. If I have got start or end is after start, then we can actually compute how long in microseconds that time was, and then with a little bit of maths, using that particular formula, which does work, I can calculate the number of millimeters that our distance is and return that. Easy. So our main application is going to be very simple. It's just going to instantiate a range sensor. It's then going to trigger. It's then going to wait just a little bit to make sure that the echoes come back, and then it's going to print out what that distance is. So let's have a look at that running in a demo and see how accurate that looks. I set this up using a ruler and a little block there to be able to see how we're doing and what measurements. So as I move the block to just under 20 centimeters, we're going to get a reading of 19 centimeters, 15 there, 14.5, not bad. Going down to 10, well actually that's reading 9 centimeters, and down to 5 centimeters, that's reading 44 millimeters. So it's not too bad. It's not perfectly accurate, but then I'm not putting that perfectly straight in front of it either, which is not helpful. But yeah, pretty good reading, certainly enough for collision avoidance, I think, on a robot. So quite a successful test. So my interest in these sensors is, of course, to use them with DDD, my DIY dev droid robot. And I'm really interested, therefore, in using more than just one of them. It's okay to know how far things are in front of you, but actually I want to know how far things are behind me, and probably left and right as well. So I'm really thinking of using 4 of these at once. It's tempting to think of using even more than 4, but actually each one of these outputs an arc of sound that is actually 30 degrees wide. And so that's expanding in size as it is going out. Now, 30 degrees apart, there is a chance that you start getting a bit of echo and noise going arc from one sensor into another. At 90 degrees, I think that's minimum, and my tests have shown actually that was fine. But if we started adding more, then they're going to start interfering with each other, and we're going to have to be really clever with strategies that we're using. To say nothing of the fact that if they're interfering and they're overlapping, then what advantage are you getting from actually measuring that distance, because you're getting interference all the time? My thoughts are that you could probably get up to 8 of these connected and not have them interfere too much, because then they're a bit 45-degree angles, and the arc coming out of them is 30 degrees of sound, so you're probably okay at that. But actually I'm going to stick to 4. The other thing to say about 4 though is connecting 4 up on a breadboard is a pain. In fact, I tried it with 2 breadboards, but then trying to get the breadboards in such a location that they're nicely 90 degrees apart and they're not causing echo to each other, I found quite difficult. So I ended up scrapping that idea and just building a dedicated circuit on a bit of prototyping board, which is what I'm doing here. I'm going to use a board it's just got all of the circuitry we've talked about already. It's much easier to do it this way. So if I wanted to now work with 4 of the ultrasound range sensors, then that's pretty easy, and I can see I've got an example here using exactly the same code. Well, I say exactly the same code. I have changed it a little tiny bit. The method's still the same that we're using, or the definition of the class, with a little bit of a change here. We also now have an alarm callback, because I didn't really like that sleep in the middle of my trigger code. So I needed to change that. So now when we do a trigger, we've split the trigger into 2 bits. So we first of all send the trigger signal to be high, and then we set up an alarm to give us a callback in 10 microseconds. When that callback fires, I do a little bit of clever stuff here to just get back into my class, and then I'm going to actually just lower that trigger. So that I feel is a little bit better than putting that sleep in there. The idea that the trigger was actually going to sleep for 10 microseconds, especially when I'm thinking of putting this into something like FreeRTOS to run with a lot of other code, makes me feel very uneasy. So I'd rather do it with a trigger callback alarm, and that all should work very nicely. So the code actually now though is really to work with 4 is very, very simple. We've now of course got a set of sensors, and although I have absolutely appalling indenting up there, let me just fix that and make that look a little bit nicer for you. So we're going to go through and trigger on the north, east, south and west direction of sensors at 90-degree angles, and those are just the GPIO pin for the trigger. The echo will be 1 more than that, so that is the way that I've done it. And so when I'm setting them up and creating them, I'm just creating them with the trigger pin is north and the echo pin will be north +1. And then we're doing exactly the same thing. I have allowed a little bit of a sleep here, just to wait until the triggers have actually completed, just to make sure that we're not getting any echo from one sensor into the other. Especially as when I'm testing this and showing it to you, I'm actually running it in a tiny little box in my photo studio, and you'll see in a minute we do actually get a little bit of bounce from one sensor to another. Generally from the ones that are either way across, so there's 2 walls either side, so you're getting echoes bouncing off walls. But otherwise the code here is pretty similar to what we did to call 1. We're just calling all 4 of them and printing them all 4 out in one go. So let's have a look at what this looks like as a demo. So with my quad board set up, I'm going to go around and place the block in front of each of the directions, starting with north, east, south and west. And we can see that each of those readings drops and we're actually getting good readings. For each of our read cycles to actually take a measurement, there's quite a bit going on in the background in terms of interrupts and the load of interrupts on our processor. So we are sending from our main code the request to trigger. That in itself is resulting in a timer callback function to actually complete the waveform of the trigger. Then, of course, we're going to monitor and listen for a rising trigger sign, and hopefully an interrupt to show that we've actually got a rising signal coming out of our sensor for the echo. And then the falling trigger is going to come back as well. So that's 3 separate interrupts that are coming down and running code and interrupting our main code. That might be not too much if we're actually only sensing once or twice a second, but when we start adding a large number of these, 4 of them or so, and we're doing it say every 1/10 of a second, this starts to get a reasonable amount of work added to our processor. Now Daniel's PIO library avoids a lot of that work. In fact, he actually reduces the number of interrupts per read cycle to 1 by using PIO. Now, if you don't know about PIO, PIO is a capability on the Pico called Programmable I/O. Basically, the Pico has 2 banks of 4 state machines which can be used to run concurrent, fairly simple code to provide interfaces out to the outside world. And that's exactly what Daniel's done. He's written a nice little PIO assembly package where we can send it a trigger, and then we will only get an interrupt back from the PIO unit once the measurement has actually been taken. So it's a really nice little bit of code, a nice way of doing it, and certainly reduces the number of interrupts that we need. Using Daniel's library to use PIO doesn't actually look that different. So over here in the code, we've got a project Quad PIO. Now I don't actually need any of the supplementary classes around it. I'm just actually using main and using his class, which is this distance sensor. So what I'm actually going to do is set up 4 distance sensors. Now I need to tell it a little bit different parameters to what we did previously, so let me just explain what these are. So when we construct the distance sensor, we need to tell it which of the 2 PIO units we want to use. So I'm doing this all on PIO 0. We need to tell it which of the state machines within that PIO it should be using, and then I need to tell it what is the trigger pin that it should use. It's going to make the assumption that the echo pin is the trigger pin +1, which is absolutely fine. And that's why I set it up for the previous example exactly like that. So we then can go through and actually initiate the trigger. The way that his library works is we need to just keep checking to see if the sensing is completed or not. And so there is a variable in each of those classes to see if it's sensing or not. Once it's finished sensing, then we actually can read the distance value directly out of the class. And that's what I'm going to do. The other slight change is this class and his class uses centimeters rather than millimeters. Not too worried about that. The accuracy on the ultrasound isn't probably millimeter sensitive, so centimeters is absolutely fine. So let's just see that this actually does exactly the same thing as the previous example, but now we're doing it using PIO. So let's just have a look at the readings this time. And I've connected everything up as the same, and you see as I'm going to go round and place the block in front of the north side. That drops that down to 7 centimeters, put it in front of the east side, dropping down to 6, south, down to 7 centimeters, and finally the west, and that's down to 5 centimeters. So that seems to work. So to compare our little strategies of using GPIO interrupts or PIO, certainly from one point of view, we can say that the PIO approach is a lot better. It uses less interrupts. It's therefore putting less load on the processor. Though, by and large, if we're only using, 1 or 2 of these sensors, we're only sensing once or twice a second, or something like that, actually the amount of difference between these is very marginal. Now, of course, I'm thinking of using 4 of these. That does start to make me wonder whether I should be using PIO and that approach is the right way to go. There is actually another dimension of this, perhaps even more important, and that's around the number of GPIOs in use. Now, both of these require 4 GPIOs triggering and 4 GPIO pins for echo response. That's quite a lot, and using out quite a lot of the available pins on my Pico. Certainly when I'm adding that to a robot, I start to get a little bit concerned, am I going to end up actually needing another Pico? So let's have a look, is there another way we could do this? And I wondered whether we could actually share the trigger pin. So could we just trigger all 4 at once and then read them all back? That way we could actually reduce the number of pins we're using, a much more scarce resource than the CPU on the Pico, I think, in this scenario, and reduce that from 8 down to 5. And that seemed to be a really interesting way to go. So I thought I'd do some experiments and see, does this work? The first thing I did was another test, taking out that sleep between the triggers, just to see if I trigger each one all at the same time, what happens? Do I start getting echo? And there is a little bit of echo going on between the east and west, but it's not remarkably different to the readings we were getting previously. So the quad GP int shared trigger is, as the name suggests, it's the GPIO interrupt strategy still, but we're now using a shared trigger pin. So if we have a look at the classes here, actually they're fairly similar. I've updated HCR range so that you have to add your first echo device or sensor device and give it the trigger pin and the echo pin for it. After that, you can keep adding additional devices just by adding additional echo pins. And then you can read the distance on any of the particular index numbers of the sensor that you want to read. If you omit that, the default is to read 0. So it's got the same interface as our base function, just with some slightly additional code into this. The code, it's going to be the same. We're doing all of the same things as we were doing previously. There isn't really very much difference in code. We just have a bit of an array now between our echoes, start and end points. And we're using the array to work out which one to give you the value and the distance of. So in our main code, which is probably the easiest way to see what's going on here, we've got my nasty indent problem again, haven't we? Sorry about that. Problem is switching IDEs on you from what I code into what I show on. Let's go and have a look though. So we've got here the range object defined, and we're going to give it firstly north, and then we're going to add east, south and west as additional echo devices. So this time I only need to call trigger once because I can just do it and all of the devices will get triggered in one go. I'm going to sleep for 100 milliseconds just to let all those range calculations be done, and then I'm going to loop through and get the distance from each of my range devices. Really nice. Let's see this work and see the demo. So the same test once again with our test board going round and placing the block in front of the north, the east, the south and the west. The readings here are really actually quite good. I think there is a little bit of echo going on between east and west, but this is in a really tight box and there is going to be some echo going on across that box. So in the real world, I think it'll be fine. That was a much deeper dive into the HC-SR04 with the Pico than I had intended. I'm fascinated by what you can do with these devices and testing them out. The debate of reaching an outcome or understanding the technology, I guess. This time I went with the understanding technology route. I think we know enough now to be able to make some decisions on how the HC-SR04 sensors will work with DDD. That means that I can look to publish the range into the ROS2 ecosystem. I'll talk through that in the next video. Thank you very much for watching. Please like the video as it helps others find it. Please subscribe and hit the notification button so you don't miss the next video. Goodbye for now.